Section 20.3 is applications of exponential and logarithmic functions. And there are actually lots of real-world examples of things that obey these models that we're studying. So many things obey what we call the law of exponential change. Things like continuously compounded interest, bacteria colony growth, insect populations, and so on. But notice this is called uninhibited growth. And we don't take the time in college algebra to study the models of inhibited growth or bounded growth, but they're out there and they're interesting also. And there's two kinds. One's called logistic curves and the other are called learning curves. So you'll probably learn about them in a later class. So the law is called an exponential law, and it looks like a sub 0 e to the k t. And the a sub 0 we call an initial value. That's the amount you start with. And k is a growth constant if k is greater than 0, and a decay constant if k is smaller than 0. And t is time. And you do have to make sure that your units of k match up with your units of time. If something is growing at 12% per year, then you need to make sure your time is in years. So let's take a closer look at a specific example, the growth in a number of bacteria in a colony. And our general formula is this a sub 0 e to the kt. But you're free to name your function whatever you like. So let's actually name it capital N for the number of bacteria. So then our function will look like N0 e to the kt. So if we begin with a formula that says N of t equals 1000 e to the 0.01 t, then that capital N gives us a number of bacteria in a culture after t hours. So after 0 hours, you can see if you put 0 in for t, that you're going to get that beginning number because e to the 0 is 1. So you get the 1000 as the beginning number. And get in the habit of writing 1000 what? So this is 1000 bacteria. So then what is the growth rate of the bacteria? There's lots of ways of looking at this, but one of the ways would be to see what happens after 1 hour. And we would have 1000 e to the 0.01 times 1. So let's see how much that is. And we get about 1010 and a little bit. So I can see that I'm growing about 10% per, and it's hour, because in 1 hour I went up about 10%. So notice that it's the e to the 0.01. E to the 0.01 is about 1.01. Oh, and let me back up. It's not 10% per hour, it's 1%, right? We started with 1,000, not 100, and we went up by 10. So 1% per hour. So e to the 0.01 is 1.01. So that's 1 plus 0.01. So this 0.01 is the growth rate. So there's lots of ways of seeing that. So C says what's the population after 4 hours? So that would be N of 4. So it's 1000 e to the 0.01 times 4. And just to make sure we can all get that same result on our calculator, I'll show you that I'm getting about 1041. My number is actually 1040.8. So I could see an argument for rounding up because it's 0.8, but it's a growth thing that's happening. And so if you go after 4 hours and you could actually count the bacteria, you would only count 1040 because this 0.8 of a 1 hasn't actually happened yet. So just something to consider when you're rounding here of think about the actual scenario and don't just round without thinking. So then D says, when will the number of bacteria reach 1700? So that's going to happen when 1700 equals 1000 e to the 0.01 t. And we know we need to isolate the exponential before we try and solve. So we're going to get 1.7 equals e to the 0.01 t. And go ahead and use a decimal if it's exact. If it's not, keep the fraction. So then we're going to use natural logs to get the t out of the exponent. That's the tool that we use. Take the natural log of both sides. Then we use that property of natural logs, or any logs, that says if I have an exponent on the argument, I can bring the exponent out in the front as a multiplier. So I'm going to have 0.01 t times the ln of e. But we're getting good at logarithms, and we know that the ln of the base is 1. So to solve for t, I'm going to divide by 0.01. So t equals exactly the ln of 1.7 over 0.1. But that's not very helpful if you're trying to tell somebody when they should go count and get 1700. So this is approximately 53 hours. And there are no rounding instructions given in this problem. I would give you specific rounding instructions, like I would say round to the nearest whole hour. Okay, and then we're asked when would the number of bacteria double. So that's going to happen when we have 2,000 bacteria when we started with 1,000. So we're going to isolate the exponential by dividing by 1,000. So I'm going to have 2 equals e to the 0.01 t. Then I'm going to use my good friends, the logarithms, to get that t out of the exponent. So I'm going to do the ln of 2 equals the ln of e to the 0.01 t, and then use the properties of logarithms that says bring that exponent out in the front, multiplying the ln of e, which we know is 1. So divide by your 0.01. So you get t is exactly the ln of 2 over 0.01. But let's figure out what that is in a decimal. And I'm getting about 69 hours if I round to the nearest whole hour. Okay, so that's if you're given the model. Here we were given a model and we were just using it to find out the answers to different questions. This second example, you're not given the model, you have to figure out the model or construct the model from the information that you're given. So let's read the words. I'll give you a moment to do that. Okay, so now we're dealing with mosquitoes. And so we have n of t is going to look like n sub 0 e to the kt. And that's all the A part is asking you for, is what would this model look like if it obeys the law of uninhibited growth? Okay, so then B, they give us some information. If there are 1,000 mosquitoes, so the N is 1,000, And so if I have 1,000 initially, so that's n of 0, well, that tells me that the n sub 0, the initial amount, is the 1,000. So you could also just get that from the words of the problem. So far I have n of t is 1,000 e to the kt. So I took care of the 1,000 mosquitoes initially. Then I'm given some more information that says there are 1,800 after 1 day. So t is in days. So n of 1 equals two things. It equals what is this equation when I put 1 in, and it also equals the number 1,800. So this is going to make it so I can solve for the k, my growth constant. So I'm going to divide both sides by 1,000 and have e to the k equals 1.8. Then I'm going to do the ln of both sides. The ln of e to the k equals the ln of 1.8. And use my property of logarithms that says k times the ln of e is the ln of 1.8. And the ln of e, of course, is 1. So we have k equals exactly the ln of 1.8. So this problem doesn't say round it to any particular value, so I would leave it exact and add this information to my model. So now I have that n of t equals 1,000, e to the k is ln of 1.8 times t. And then we're asked what is the size of the colony after 3 days. So we're being asked to use our model and put 3 in for the t. And you may have to put parentheses around that exponent on your e to make sure your calculator does what you think it's doing. And I'm getting about 5832 mosquitoes after 3 days. Okay, and then we're also asked how long until there are 10,000 mosquitoes. So how long is asking us to solve for t. So we write out 10,000 equals, what does the function look like if I have a t there and I want to solve for the t. So I'm going to divide both sides by 1,000 and get 10 equals e to the ln of 1.8 t. Then I'm going to do the ln of both sides. The ln of 10 equals the ln of e to the ln of 1.8 t. And use my property of logarithms that says this exponent can come down in the front. And I'll have the ln of 10 times the ln of 1.8 times t times the ln of e. But I know the ln of e is 1. So I'm going to solve for t by dividing by the ln of 1.8. ln of 1.8. So t is going to be approximately 3.9 days. Okay, so that was exponential growth. And we also are going to look at exponential decay. And the example that comes up the most often is radioactive elements that decrease in mass over time. So let me go ahead and stop the video here, and I'll resume in a second video so that they stay nice and short.